Hello friends, welcome back to my channel. Today I would like to talk about halogen compounds, which is also called halogenoalkanes. Halogenoalkanes or alkyl halides are compounds in which one or more hydrogen atoms in an alkane have been replaced by halogen atoms, fluorine, chlorine, bromine or iodine. Example, chloropropane, 2-bromopropane. Halogenoalkanes can be classified as primary, secondary or tertiary depending on the number of alkyl groups, R groups, attached to the carbon atom holding the halogen atom. As you can see here, the first one is primary, 1 R group or 2 hydrogen atoms. Secondary, 2 R groups or 1 hydrogen atom. Tertiary, 3 R groups or no hydrogen atoms. Making halogenoalkanes. These are the reactions. We will see one by one. The first one, free radical substitution of alkanes by chlorine or bromine in the presence of UV light. C2H6 plus Cl2 in presence of UV light, you get C2H5Cl plus HCl. Second reaction, the electrophilic addition of an alkene with a halogen X2 or a hydrogen halide HX at room temperature. C2H4 plus Br2 gives C2H4Br2. Third reaction is substitution by an alcohol. For example, the reaction with HX or with KX and H2SO4 or H3PO4 to make HX. CH3CH2OH and HCl give CH3CH2Cl and H2O. With PCl3 and heat, 3C2H5OH plus PCl3 in presence of heat, you get 3C2H5Cl and H3PO3. With PCl5 at room temperature, the reaction is C2H5OH and PCl5 gives C2H5Cl plus HCl plus POCl3. With SOCl2, which is thionyl chloride, the reaction is C2H5OH plus SOCl2 gives C2H5Cl and HCl and SO2. Now comes the physical properties of halogenoalkanes. Boiling point of the halogenoalkanes increases as the molecular size increases. This is because there are more electrons in larger molecules and more temporary dipoles can be set up, resulting in stronger van der Waals forces. Primary halogenoalkanes have higher boiling point compared to secondary and tertiary halogenoalkanes of the same molecular weight. This is because the surface area of primary halogenoalkanes is higher, more temporary dipoles can be set up, resulting in stronger van der Waals forces. The second property, halogenoalkanes are insoluble in water but soluble in organic solvents. This is because when dissolved in water or polar solvents, the energy needed to break the hydrogen bonds between water molecules is too high. The energy released when halogenoalkane water attraction is set up is not enough to compensate it. This makes the structure to gain energy overall, making it less stable. While when it is dissolved in organic solvents, the halogenoalkane solvent attraction is strong enough to compensate the energy needed to break the weak van der Waals forces between organic molecules. Test for halogenoalkanes. We use acidified silver nitrate solution to test for halide ions. Remember that aqueous chlorides gives a white precipitate, which is silver chloride. Bromides give a cream precipitate, which is silver bromide. Iodides produce a pale yellow precipitate, which is silver iodide. Reactions of halogenoalkanes. The trend in the reactivity of the halogenoalkanes is shown below. Fluoroalkanes, which is least reactive, to the most reactive iodoalkanes. The substitution reaction involves the breaking of the carbon-halogen bond. The bond energy values help us to explain the rates of reaction. And from the table, you can notice that the Ci bond is the weakest, so it is broken most easily. Nucleophilic substitution reactions. A nucleophile is a species, an ion or a molecule which is strongly attracted to a region of positive charge in something else. It normally carries either a partial or fully negative charge on the molecule. Some examples of nucleophiles are shown below. OH minus, Cn minus, OH2 which is water, H2O, NH3 which is ammonia. Nucleophilic substitution reactions with aqueous alkali OH minus and heat to produce an alcohol. When an aqueous solution of sodium hydroxide is heated with a halogenoalkane, a nucleophilic substitution reaction takes place. The halogen atom in the halogenoalkane is replaced by OH, a hydroxyl group, so the organic product formed is an alcohol. As you can see here in the equation, bromoethane and NaOH gives you ethanol and NaBr. The aqueous hydroxide ion behaves as a nucleophile here because it is donating a pair of electrons to the carbon atom bonded to the halogen in the halogenoalkane. The next reaction is a substitution reaction with KCN in ethanol and heat to produce a nitrile. In this reaction, the nucleophile is the cyanide Cn- ion. To carry out the reaction, a solution of potassium cyanide KCN in ethanol, known as an ethanolic solution of potassium cyanide, is made up. This is then heated under reflux with the halogenoalkane. An ionic equation for this reaction is bromoethane plus Cn- gives propane nitrile and Br-. Note that the reaction with the cyanide ion adds an extra carbon atom to the original haloalkane carbo chain. In this case, bromoethane is converted to propane nitrile. The next reaction is substitution with ammonia in ethanol heated under pressure to produce an amine. If we heat a halogenoalkane with an excess of ammonia dissolved in ethanol under pressure, an amine is formed. Bromoethane plus ammonia gives ethylamine plus HBr. Here, the nucleophile is the ammonia molecule. The organic product, ethylamine, is a primary amine as the nitrogen atom is attached to only one alkyl group. If the ammonia used is not in excess, a complicated mixture containing secondary and tertiary amine is obtained. This is because ethylamine is a good nucleophile and it can attack the unreacted bromoethane. The next is the reaction with aqueous silver nitrate in ethanol as a method of identifying the halogen present, as exemplified by bromoethane. Halogenoalkanes can be broken down under reflux by water to form alcohols. The breakdown of a substance by water is also called hydrolysis. This reaction is classified as a nucleophilic substitution reaction with water molecules in aqueous silver nitrate solution acting as nucleophiles, replacing the halogen in the halogenoalkane. For example, bromoethane reacts with aqueous silver nitrate solution to form ethanol. As you can see here, the mechanism is shown. C2H5Br and water under reflux give C2H5OH and HBr. Mechanism of nucleophilic substitution in haloalkanes. Nucleophilic substitution is done via two mechanisms, the SN1 and SN2 mechanism. Primary halogenoalkanes will use SN2. Tertiary halogenoalkanes will use SN1. Secondary halogenoalkanes will use both. So at first, let's see the mechanism for primary halogenoalkanes, which is SN2. In SN2 mechanism, the S stands for substitution, the N stands for nucleophilic, and the 2 stands for the initial step, which is a rate determining step, involves two species. The the halogenoalkane and the nucleophile. The general mechanism of an SN2 reaction using bromoethane CH3CH2Br as a typical primary halogenoalkane and nucleophile as a general nucleophile. The carbon-bromine bond is bromoethane is polarized. Next, the nucleophile is attracted towards a positive carbon. Meanwhile, the negative bromine atom is repelled further due to the approaching nucleophile. Eventually, there is a state called the transition state where the carbon-bromine bond is just at the point of breaking and the carbon-nucleophile bond is just at the point of forming. The movement goes on until the nucleophile is firmly attached to the carbon and the bromine has been expelled as a bromide ion. The nucleophile has substituted the bromine. You can see the mechanism over here. When the nucleophile approaches a halogenoalkane, it approaches from the opposite side of the bromine because the negative bromine hinders the attack from its own side. It is crucial to get the orientation of the atoms right. The molecule has been inverted at the end of the reaction. This is called the inversion of configuration. Product has a configuration opposite to the reactant. Let's see the mechanism for tertiary halogenoalkanes, which is SN1. In SN1 mechanism, the 1 stands for the initial step, which is a rate determining step, involves one species only, the halogenoalkane. The overall rate of reaction is governed by the rate of the first step. The general mechanism of an SN1 reaction using 2-bromo-2-methylpropane CH3 thrice Br as a typical tertiary halogenoalkane and Nu- as a general nucleophile. The reaction happens in 2 stages. In the first stage, a small proportion of the halogenoalkane ionizes to give a carbocation and a bromide ion. As you can see here, this is a slow step. Once the carbocation is formed, it will react immediately when it comes into contact with a nucleophile. The lone pair of the nucleophile is strongly attracted towards a positive carbon and move towards it to create a new bond. And here, that step is a fast step. Tertiary halogenoalkanes react via SN1 because the tertiary carbocation intermediate form is relatively stable. If primary halogenoalkanes were to react in the same manner, the primary carbocation formed would be relatively unstable, resulting in high activation energy of the reaction. Secondary halogenoalkanes can react using both SN1 and SN2 mechanisms because the opposite of the halogen is not cluttered by CH3 group. Secondary carbocation form is more stable than primary carbocation. The next reaction is elimination reaction. Halogenoalkanes also undergo elimination reactions. An elimination reaction involves the loss of a small molecule from the original organic molecule. In the case of halogenoalkanes, the small molecule is a hydrogen halide such as HCl or HBr. The reagent used in these elimination reactions is ethanolic sodium hydroxide heated with the halogenoalkane. As you can see here, bromoethane and ethanolic NaOH in presence of heat gives ethene plus water and NaBr. The original bromoethane molecule has lost a hydrogen atom and a bromine atom. We can think of it as HBr being eliminated from the halogenoalkane. The ethanolic OH- ion acts as a base, accepting a H+ ion from the halogenoalkane to form water. The CBr bond breaks heterolytically, forming a Br- ion and leaving an alkene as the organic product. That's all. Thank you so much for watching this video.